let's look at number 44. This time, they want us to find the normals to the curve, xy plus 2x minus y equals 0, that are parallel to the line 2x plus y equals 0. Okay, so this is quite similar to what we just did, but they've given the information somewhat more indirectly. They want normals to the curve. Okay, so we'll take the derivative. That'll give slopes of tangent lines. We'll need a negative reciprocal of that to get slopes of the normals. And then we'll want those slopes to be parallel to the line, the same as the slope of this line. So it's nothing fundamentally new, it's just information presented in a different way. So let's find dy dx by differentiating implicitly. And you might observe, hey, can you solve for y in terms of x in this one? You know what, I bet you can for a change. I bet you could solve for y in terms of x. Now that doesn't necessarily mean that's any easier to deal with. Let's do it with implicit differentiation because that's what we're illustrating. But, you know, unlike the previous ones, maybe you could solve for y in terms of x in this one, and you could skirt around the use of implicit differentiation. Let's do it implicitly anyhow. It's not bad to do the implicit differentiation, and because this one's relatively uncomplicated. So we'll differentiate xy plus 2x minus y, and we'll differentiate 0. Differentiate implicitly both sides of the equation. All right, that'll require a product rule here. We've got a product of functions of x itself, and y, the function implicit to that equation. So we'll need the derivative of x with respect to x is 1 times the second times y plus the first x times the derivative of the second. Derivative of y with respect to x is the thing we're looking for, the dy dx. Next, differentiate 2x. That just gives us 2 times 1, if you like. Next, differentiate y with respect to x, dy dx. And on the right-hand side, of course, we have 0, the derivative of 0. Cleaning it up a little, we've got y plus 2. Here's a dy dx times x. Here's a dy dx times negative 1. So we can do a little factoring there. Move the y plus 2 to the right-hand side. It becomes negative. Divide by x minus 1. Maybe manipulate the negatives a little bit. And we can solve for dy dx as y plus 2 over 1 minus x. So at some point, x1, y1 on the curve, xy plus 2x minus y equals 0. The slope of the normal line is negative 1 over normal line, the derivative evaluated at x1, y1. The derivative evaluated at x1, y1 is the slope of the tangent line. Negative 1 over that is the slope of the normal line, and we're interested in normal lines. All right, so plug in x1, y1 in here and take a negative reciprocal. Plugging in, we'd have y1 plus 2 divided by 1 minus x1, but we'll have a negative out front and we'll take a reciprocal of that, producing negative 1 minus x1 divided by y1 plus 2, negative reciprocal. So that's the slope of normal lines. They want normal lines to be parallel to this line. Parallel lines have the same slope. What's the slope of this line? Well, the slope of 2x plus y equals 0 is negative 2. Write it as y equals negative 2x if you like. Then we've got a y equals mx plus b situation. If you like your capital AX plus capital BX equals C style of a line, which this is, the slope's negative A over B. No matter how you slice it, you get a slope of negative 2. So for the point x1, y1, we look for the point x1, y1 such that this, the slope of a normal line, equals that, equals negative 2. So we want negative 1 minus x1 divided by y1 plus 2. We want this to equal negative 2. We can say cross multiply by y1 plus 2, maybe get rid of those negative signs, multiply both sides by negative 1. That gives us 1 minus x1 equals 2, y1 plus 2. Distribute, rearrange, leave it to you to go through all the algebraic details, but we get x1 equals negative 2 y1 minus 3. So there's x1 in terms of y1. But I need both of them. I need x1 and y1. That information we got from the slope information, the normal to the curve stuff. This point x1, y1, talking a normal to the curve, this will have to also be a point on the curve, xy plus 2x minus y equals 0. And we haven't used that information about x1, y1 yet. The x1, y1 we used in connection with a slope, not in connection with the fact that this is a point on the curve. So next slide, we'll keep this information in front of us. X1 is negative 2, y1 minus 3. Yeah, but also x1, y1 lies on the curve. xy plus 2x minus y equals 0. So let's substitute this information into that equation, but do it in a way that only involves one of the variables. We know x1 in terms of y1. So if we plug x1, y1 into this curve, we'll have x1, y1 plus 2x1 minus y1 equals 0. x1, let's see, x1 is this. So here's x1 times y1 plus 2x1 in this form minus y1 equals 0. So we've replaced the x1s with this representation of it. What we got right here, that's an equation involving only y1s. So we can solve that for y1. So that's how we'll find y1. And then we got a couple ways we could go back and find the x1s. Let's see, distributing, this gives us a negative 2y1 squared minus 3y1 minus 4y1 minus 6 minus y1 equals 0. That's a negative 2y1 squared minus 3 minus 4 minus 1. That's minus 8 y1s. Yeah, minus 8 y1s. We still got the negative 6 there and a 0 on the other side. Looking for something I can factor. How about we divide through by negative 2? That'll leave us with a y1 squared plus 4y1 plus 3. y1 squared plus 4y1 plus 3 equals 0. And that I can factor. So they gave us nice numbers, it turns out. And we can factor that into y1 plus 3 times y1 plus 1 equals 0. So we need either this term to be 0, that is we need y1 to be negative 3, or this term to be 0, that is we need y1 to be negative 1. Now that we know y1, two possible values for y1, we need to find the corresponding values for x1. It looks like there'll be two such points for in answer to the question. So take the y1s and plug them into this equation if you like. We've also got an equation up here that relates x1 and y1. But plug y1 equals negative 3 into this equation. You'll find x1 is 3. Plug y1 equals negative 1 into this equation, say. You'll find x1 is negative 1. So we've got 2 points. We've got the point 3, negative 3, and the point negative 1, negative 1, as points on the curve where the slope of a normal line will be the same as the slope of this line. That is, we'll have normal lines parallel to the given line. So the desired normal lines contain the points 3, negative 3, and the other one contains the point negative 1, negative 1. So we've got 2 lines, 2 points. In both places, we'll have a slope of negative 2. Using the point slope formula, first with the point 3, negative 1, and the slope negative 2. 3, negative 3, and the slope of negative 2 produces the line y equals negative 2x plus 3. Using the point negative 1, and the slope negative 2 produces this line here. I'll leave it to you to pause it and think through the arithmetic and the substitutions. But these 2 lines both have slopes negative 2. You're right, that makes them parallel to this line, which has slope negative 2. And these lines at the given respective points are normal to this curve. That's where the points came from, was dealing with normal to the curve. So there's another one involving normals to a curve. Let's go back to the notes. one more comment, and then we'll do a handful more examples. And just as we can use the chain rule to find the derivatives, we can find higher order derivatives. So we can find second and third order derivatives and so forth using implicit differentiation. Thing is, it'll just be repeating the process we already had, except this time we'll need to introduce a second derivative, a d squared y dx squared kind of thing. We'll need a second derivative when we differentiate implicitly a second time. So that's best explained just with some examples. Here's an equation. They want you to find dy dx and the second derivative of y with respect to x for y, an implicit function to this equation. Okay, I bet you there's more than one function implicit to this equation because we're looking at a y squared and an x squared term. Ultimately, there's some other stuff there too. But I don't think this determines a single function. Y is a function of x. So we're forced to differentiate implicitly, differentiate both sides of the equation implicitly with respect to x. Derivative of x to the 2/3 with respect to x. 2/3 x to the negative 1/3. If you want to put a dx there, I can't argue against it. It's not pretty. It's not what the rest of the world does, but it's not wrong. And it is a consistent way to treat the variables. Differentiate y to the 2/3 with respect to x. We get 2/3 y to the negative 1/3, subtract 1 from the exponent as we did over here. And now you have to multiply by dy dx. So that one's not optional there. Chain rule told you to do that because you got a composition of functions. Which functions are composed? What's the composition here? What's the outer function? 2/3. We differentiated it, right? That's where the 2/3, 2/3 minus 1, negative 1/3. That's where that stuff came from. What's the inner function? Y. Y is an implicit function of x. So we got a composition of functions, thus the chain rule. That gives us a dy dx. You can't leave the dy dx off because that's what you're looking for. Right-hand side, we just get derivative of 1 is 0. And usual stuff, rearrange, solve for dy dx, and we get, say, this version here. You want to simplify it? Probably so, because we're going to try to find a second derivative. So let's clean it up as much as we can. The only real change from here to here is getting rid of some negative exponents. But here's dy dx in one particular form. How are you going to find the second derivative? Well, differentiate both sides of this. That'll produce the second derivative on the left-hand side. Let's see what happens on the right-hand side. Looks like a quotient, eh? So we'll take a derivative with respect to x of dy dx and a derivative with respect to x of this stuff here. That produces a second derivative of y with respect to x on the left-hand side. Here, be very careful, I need a quotient rule. First, let's bring that negative sign out front. Looking at my square brackets, round brackets, minus round brackets, square brackets over round brackets squared, I see my picture of the quotient rule. Be careful, y is a function of x. Oops. We'll need some chain rule stuff. We'll need the derivative of the numerator. That's a composition of functions of x. The outer function's the 1/3 power function, and the inner function is y, a function of x, implicit to the equation. I don't know what it is explicitly. Okay, so we'll have then 1/3 y to the 1/3 minus 1. That is y to the negative 2/3. Chain rule makes you stick a dy dx over there. Okay, we got the second derivative of y with respect to x. It's going to equal all this stuff here. Do you know what dy dx is? Oh yeah, we found that in the first part. So we'll substitute for that here down the road. We're in the middle of the quotient rule. That's derivative of the numerator. Here's the denominator, the x to the 1/3, minus numerator, y to the 1/3. Derivative of the denominator. It's a function of x. Differentiate with respect to x. Bring the exponent down, subtract 1. So there's the derivative of the denominator over the denominator squared. So quotient rule combined with some chain rule stuff gives us a second derivative. Yeah, it introduced some more dy dx stuff. It's okay. I know what dy dx is in terms of x's and y's. So here's where we left off on the previous page. It's cleaned up a tiny little bit. Let's clean it up a little bit more and get rid of some of those square brackets. So let's see, we've moved the x to the 1/3 over. So we got a power of x times a power of y, the dy dx. Here we brought the number out front, power of x times power of y. Denominator we've, as it were, multiplied out. Okay, let's get rid of this dy dx because I know what dy dx is. That was the first part of the question. So copying what we had from above, we had dy dx is negative y to the 1/3 over x to the 1/3. Stick that in there. You want to say that's the second derivative, fine by me. I guess I could clean it up a little bit. Here's an x to the 1/3 and here's an x to the 1/3. I could cancel those two. And I could multiply y to the negative 2/3 times y to the 1/3, leaving us with a y to the negative 2/3. I got a negative here and a negative out front. I could simplify that. I'm actually happy with it in this form here, but it can be cleaned up a little bit and it could be further modified from there. So it's a matter of taste as to how you express the second derivative, but there's the second derivative. So how do you find second derivatives implicitly? You find first derivatives and then differentiate those. In doing so, you may have some more first derivatives appear. So you know what the first derivative is in terms of x and y. Answers should be in terms of x and y. You know what the first derivative is because that was the first part of the question. Substitute in, and you're good to go. A couple of others. Question 48 talks about the folium of Descartes. It says, find the slope of the folium of Descartes with equation x cubed plus y cubed minus 9xy equals 0 at the points 4, 2 and 2, 4. They want the slope. Okay, that's a derivative. What else they want? At what point, other than the origin, does the folium have a horizontal tangent? Horizontal tangent. Looks like it's got a horizontal tangent here. Actually, it passes through this point twice. So there's a horizontal tangent one time. It's okay, it's got a vertical tangent the other time. We'll see that pop up in our computations. Part B was there's another horizontal tangent. Yeah, it's somewhere up here. It looks like somewhere up here it's got a horizontal tangent. And in part C, they asked for the coordinates of point A in this picture where the folium has a vertical tangent. Point A. Okay, so they're saying it's got a vertical tangent somewhere over here, and they want us to find the coordinates of that point. Okay, so they've given us a graph in the figure. First part, find the slope at particular points. Piece of cake. We'll differentiate implicitly and plug in the coordinates of those 2 points they're interested in. Differentiate implicitly both sides of the equation. Should be routine by now. Differentiate x cubed with respect to x, 3x squared. Differentiate y cubed with respect to x, 3y squared, dy dx. Chain rule adds this in. Differentiate is treated as -9 times xy. Let's bring the -9 out front. Differentiate the product x times y requires the product rule. Derivative of the first, derivative of x is 1 times y plus first x times the derivative of y with respect to x equals 0. I can probably skip a step of algebra here, rearrange that, getting the dy dx's. Let's see, this one's times 3y squared. This one, when I distribute, is times -9x. Yeah, 3y squared, -9x. dy dx, take the other terms to the right-hand side. They go to the right-hand side as negatives of what they were on the left-hand side. Produces this. Very little algebra skipped there. Next, we'll divide by this coefficient, and that'll give us dy dx in terms of x's and y's. Slide 2. We left off here, divide, and that gives us dy dx is this quotient here, provided we haven't divided by 0. So I need to say somewhere that denominator is not 0. Now they were talking about some vertical tangents somewhere in there, so we maybe haven't seen the last of this concern over the denominator being 0. Slope of the curve at 4, 2 would simply be the derivative, which we just computed, evaluated at 4, 2. I plug 4's in for x's. here and here, yeah, here and here, and 2's in for y's, here and here. I do the arithmetic, I get 5/4. They wanted to know the slope of the curve at 2, 4. At 2, 4, it's got a little typo here, at 2, 4. Evaluate the derivative at 2, 4. Sorry, I'll fix that in the notes. Should read 2, 4. That was the second question, 2, 4. I've plugged the numbers in correctly, so we're all right. But I'll fix that typo. So we plug in 2 for x. There's a 2 for x, the 4 for the y. Do the arithmetic. We get 4/5. I wonder if that's a coincidence. There's some sort of symmetry to this graph. More of that in a little while. But we get a slope of 5/4 at 4, 2, and we get a slope of 4/5 at the point 2, 4. And that was part A. At what point, other than the origin, does the folium have a horizontal tangent? All right, horizontal tangent means the derivative is 0. So we'll set the derivative equal to 0. The problem is the derivative involves both x's and y's. So it's a little more complicated than when we set derivatives equal to 0 back in the setting of explicit functions. Okay. So we'll take the derivative, evaluate it, let's say at point x1, y1. So that'll be the point where we have a horizontal tangent. So we'll plug those in for the x and y values, set it equal to 0. Now, the only way we can have a quotient equal to 0 is when the numerator is 0 and the denominator isn't. We've already made a comment about that. So we'll have the numerator equal to 0. 9y1 minus 3x1 squared equals 0. Solving for y1, say we get y1 equals, take this to the other side, divide by 9 and simplify. We get y1 equals x1 squared divided by 3. So that's a requirement for the derivative to be 0. We know this point, this is similar to the previous one, this point x1, y1 also lies on the equation there, x cubed plus y cubed minus 9xy equals 0. So as in, maybe it was the previous one, there's two questions back. As in that former question, let's plug in x1 values for x and y1 values in terms of x. This time we got y1 in terms of x. I think last time we had x1 in terms of y. But I just want a single variable here. So we're plugging x1 in for x, and we're plugging y1, this version of y1, in for y. So we'll have x1 cubed, plus this thing here cubed, because this thing here is y1, minus 9x1 times that, minus 9x1 times that, x1 squared over 3. All right, so that produces this equation. We're looking for x1. Once we find x1, we can find the corresponding y1. This simplifies down to, what have we got, x1 cubed. Cubing this, we'll have an x1 to the 6th over 3 cubed, it's 27. We get an x1 cubed from this, 9 divided by 3 is 3, leaves us with that, which simplifies a little bit more to x1 to the 6th over 27 minus 2x1 cubed equals 0. We can factor an x1 cubed out. Factoring an x1 cubed out, we're left with an x1 cubed over 27 minus 2. So we got it factored. We got a product of two things set equal to 0. That means either x1 equals 0 or x1 makes this 0. We need x1 cubed to be 54. So we need x1 to be the cube root of 54. In which case, indeed, this would be 54 over 27 is 2 minus 2, gives us 0 out. Alternatively, we could write that as 3 on the cube root of 2. Take the 3, cube it, and put it inside, and you'll be looking at the cube root of 54. So this is the right x1 value to make that term 0. All right, so we got 2 points where we have a horizontal tangent. They want the point other than the origin, and they got their reasons for that. It's because it passes the origin twice is their reason. When x1 equals 0, we can plug into the equation and see that y1 would have to be 0 as well. So yeah, this actually reveals that we do have a horizontal tangent at the origin, but they want us to find the other one. Okay, so it must be the one where x1 is 3 times the cube root of 2. So plug in 3 times the cube root of 2 into that. How about this formula here? Plug in x1 is 3 times the cube root of 2. That'll tell us the corresponding y1 value. There's the arithmetic. We'll get 3 times the cube root of 4. So it looks like that tangent occurs at the point x1, y1 is the values we found. x1 is this and y1 is that, as given here. So there's the coordinates of the other point where the curve has a horizontal tangent. Okay. Not particularly ugly numbers, cube root of 2, cube root of 4. That it could be a lot worse. Not pretty little integer values. Yeah, dealing with these complicated equations, it's unlikely you're going to get pretty little integer values. You're lucky it ain't worse than this, it turns out. So I'm grateful it's only cube roots of 2 and cube roots of 4 is our weird numbers. But the arithmetic checks. And there's the place where we'll have a derivative of 0. All right, part C, they want us to find the coordinates point where it had a vertical tangent. All right, here's what we had for the derivative upstairs. So we want to know where this yields a vertical tangent. If you go back and look at limits involving infinities and asymptotes of graphs, where we talked about infinite limits, and also we talked about vertical tangents in section 3.1, this is going to occur, if at all, where the denominator is 0. So let's take that denominator, let's take this derivative, plug in x1, y1, get some specific values to deal with, and let's set the denominator equal to 0 and see what happens. That gives us x1 equals y1 squared over 3. So there's a relationship between x1 and y1, again, this time looking at the denominator, before looking at the numerator. Since x1, y1, but it's going to have to be a point on the folium of Descartes. It's got to satisfy this equation. So again, we'll plug in like we did before. This time we'll plug in x1, this stuff here, and we'll plug in y1 for y. So x cubed becomes x1 cubed. I mean, this thing cubed, y1 squared over 3 cubed, plus y1 cubed, substituting for y, y1, minus 9 x1, y1, but I'll write the x1 in terms of this, and it produces this term here. Let me skip some algebra here. Multiply out, simplify, and factor, it produces this. So we need either y1 equals 0, or we need this thing equals 0. This thing equals 0, lo and behold, it's when y1 equals this, it's also the cube root of 54. That's what we get from this one as well. The x's and the y's are playing some kind of symmetric role, it seems. We'll draw a picture at the end, or look at the picture again and talk about symmetries. But what we'll get is either y1 is 0 or y1 is this value here. Hey, when y1 is 0, then x1 is 0. We're talking about the origin. They're talking about point A, and point A was not the origin. It was somewhere on the right-hand side of the graph. So we can discount the origin given the kind of question they asked. So we see that we have a vertical, when y1 equals, here we go, y1 equals the cube root of 54. We have x1 equals this value here. That's the point we're interested in. At the origin, we have both a horizontal and a vertical tangent line. We commented about that at some point earlier. So that's not what we're interested in. The y1 value produces this corresponding x1 value, and this x1 and that y1, that must be the coordinates of point A. That must be the coordinates of point A, so point A is given by this. Now, numerically, the 3 times the cube root of 4 is like a couple of decimal places, 4.76. That looks about right in terms of the picture they've given us. It looks ballpark for part A. So I think that's consistent with the graph. But some things happened in terms of these horizontal and vertical tangents. I claim if we were to draw the line y equals x, this graph is symmetric with respect to the line y equals x. Over here, where we had the vertical tangent, somewhere up here, there's a corresponding horizontal tangent. We had the vertical tangent at 3 times the cube root of 4, comma, 3 times the cube root of 2. And we had the horizontal tangent at 3 times the cube root of 2, comma, 3 times the cube root of 4. Interchange these two coordinates, get those two coordinates. Interchange, or fold this thing over about the line y equals x, that interchanges x's and y's. It also sends horizontal lines to vertical lines. When we looked at inverse functions, we saw some behavior like that. So it's not a coincidence that what happened for this vertical tangent is in some way related to what happens where there's a horizontal tangent. It's some kind of symmetry. It's symmetry of the graph with respect to the line y equals x is what it is, to put a precise label on it. But that answers the questions they had about this one. Like I said, geez, the numbers could be a lot worse when you're dealing with these equations. We're lucky it only involves some cube root stuff, but it turned out to be relatively nice cube root stuff. And there was even some symmetry. The work we did on a couple of those slides was repetitious. Yeah, we were doing the same thing for y that we did for x, or the same thing for y sub 1 that we did for x sub 1 because of that symmetry, it turns out. And one final thing from this section is a power rule for rational exponents. And what we're doing is slowly establishing the power rule for all real numbers. In the beginning, we established that the derivative of x to the n is nx to the n minus 1 when n is a positive integer. In one of the homework exercises, we showed it also holds when n is a negative integer. We use the quotient rule to show that. Now we're showing it using implicit differentiation, that's why we're doing it now, when the exponent is a rational number. So let p and q be integers, say q is positive, so if there's any negativeness, give it to p. If y equals x to the p divided by q, differentiate the equivalent equation, y to the q equals x to the p, just raise both sides to the q power. Differentiate this equation implicitly and show that, for y non-zero, the derivative of x to the pq equals p over q, x to the pq minus 1. Okay. First, y equals x to the pq holds if and only if we raise both sides to the q power and get y to the q equals x to the p over q to the q. Multiply exponents in that setting, and that establishes the equation y to the q equals x to the p, where y is some function of x. In fact, it's this function here, which you, depending on how you approach the logic of it, we don't know how to differentiate x to the p over q yet. That's what we're establishing. We've made a bold claim about how to differentiate x raised to any power. We've only established it so far for integers. Now we're establishing it for rational numbers, thus the rational exponents label on this. So we get y to the q equals x to the p. Differentiate both sides implicitly with respect to x. Are we okay on that? Can you differentiate x to the p where p is an integer? Yeah, we proved how that works. And it's no surprise how it works. You bring the exponent down, you subtract 1 from the exponent. So when we differentiate x to the p with respect to x, we get p x to the p minus 1. And we've established that because here p is an integer. And we know this holds for integers. We're about to know it holds for rational functions. On the left-hand side, we've got a composition of functions. And here we've got the function y of x raised to the q power. Q is an integer. In fact, it's a positive integer, and we know what to do with that. You bring the exponent down, you rewrite the inner function, you subtract 1 from the exponent, and then the chain rule makes you multiply by the derivative of the stuff inside, the derivative of y. With respect to x, we're differentiating with respect to x. Don't forget the dy dx. What are you looking for? I'm looking for the dy dx, so don't leave it out. So differentiating implicitly, we get this equation. There's the thing we're looking for. So all we got to do is get this stuff out of the way and simplify. So divide both sides by q y to the q minus 1. That'll give us dy dx equals the right-hand side divided by q y to the q minus 1. Okay. You know, we had an explicit form for y in terms of x. Let's substitute that in. So let's replace the y with x to the p over q. So this can be rewritten, dy dx equals, same numerator, q, replace the y with x to the q over p. Still got the q minus 1 exponent outside. We can multiply exponents here. So take q minus 1, multiply by p over q. Q times p over q is p. Negative 1 times p over q is minus p over q. So multiply exponents in that case, common exponential raised to a power, multiply exponents. All right, we got a p over q. Let's pull that aside, remember where we're going with this. And we've got a power of x in the numerator of p minus 1, a power of x in the denominator of p minus p over q. Subtract exponents when dividing, property from high school, really. Now, when we simplify, we've got p minus p, so the p's are gone. We got a negative minus a negative p over q. So what we're left with is, let me try that again. We got a negative minus p over q, leaving us with a p over q. So the p's have canceled. We got a positive p over q and a minus 1. We got a positive p over q and a minus 1. And that's what we were supposed to get. So if you differentiate a power of x where that exponent is rational, then you bring the exponent down and subtract 1 from the exponent. What a horribly unsurprising result. Maybe the only real surprise is we had to show that. Yeah, we hadn't demonstrated that yet. We've made some bolder claims about what happens even when we have irrational exponents. And really, that's a conversation, in my opinion, that should wait for Calculus 2 when you know more about exponential functions. You'll formally define logs and exponentials in Calculus 2. We're using an early transcendental edition of the book, and we started talking about irrational exponents, in my opinion, a little prematurely. But it turns out they behave the same way as rational exponents and as integers. So that completes section 3.7, and that completes implicit differentiation. We're about to use implicit differentiation on some applied problems. So what good is this stuff? Well, we're about to do a bunch of applications involving derivatives as rates of change with respect to time, and we'll deal with equations that relate things that change with respect to time. We'll have to differentiate implicitly because we may not know what those functions of time are explicitly. And that'll be some of the more challenging stuff in Calculus 1. And unfortunately, it's also some of the more applicable stuff in Calculus 1. So I will see you soon in section 3.8. Have a nice day.